Good afternoon, everybody. Thank you very much for turning up and listening to me waffle about fish welfare, which I'm an advocate of. I'm a welfare scientist as well. I represent various organisations, but in particularly today, Anglia Ruskin University and the Aquarium Welfare Association. So as you might have gathered, I'm going to try and make a case for why we should care about fish suffering or the ability of fish to feel pain or their relative sentience. And it'll be fun, hopefully, and full of good citations and references, so it'll be very much evidence-based. Okay. So making the case, when I talk about aquatic animals, I'm not talking about cetaceans. They obviously have their own issues in captivity and are well understood with regard to their cognitive ability and likely suffering in captivity. So what I'm really interested in is animals that are obligated to breathe in water. So that doesn't include otters, it doesn't include penguins. It really is animals that are obliged to use water as an absolute necessity in their lives. Okay? So I'm going to hopefully convince you that aquatic animals are capable of high levels of cognition. Also, what the evidence for this cognition and where it lies. It's all very new, this. Scientists and the public alike are struggling to keep up. Then I'm going to speak about the likelihood of aquatic animals to actually suffer, which might be new to some of you, although the evidence is now quite strong. And also some problems of captive living that I've come across and how my research has made a tiny dent into what is an ocean of problems, really. Excuse the pun. Okay, so fish. Everyone thinks they're stupid, or at least they did until very recently. There's still a lot of misunderstandings about the abilities of fish. People still think, and when I talk about people, I don't talk about the highly educated amongst you, and you all are clearly highly educated. It's more about the public generally that I'm talking about. And people do think still that fish only possess 3-second memories. People assume fish can't think. They are essentially automatons. And as I'll show you by evidence-based publications, these myths have been seriously busted in the last 10 years. None of these are true, and hopefully you won't think that. And I'm really trying to get the public to also understand. So part of my work is advocacy regarding the evidence that I'll show you. So as far as fish cognition goes, the elephant-nosed fish, which is a wonderful name for a fish, it's got a very long snout. It's electrical sensitive, so it hunts out its prey using a very highly sensitized nose area. It's a freshwater fish, and it has the largest brain-to-body weight ratio of all vertebrates. Now, we don't expect or presume that body-to-brain ratio is the exact measure of cognition. That is now quite an old idea, but nevertheless, it gives you an idea of the neural complexity within what is quite a small fish. Also, there's strong evidence to suggest that intertidal gobies in particular have incredible memories. They're able to remember specific rock pools. Now, if you've been to the rocky shore recently, you will no doubt recall that it's a mosaic, a very complex mosaic of rock pools which can change and also are very difficult to distinguish, at least from our eyes. But intertidal gobies have remarkable memories and are able to remember where to go back to at each low tide. And it does require a very significant memory ability, which is part of cognition. And there's good evidence for this. And again, 2015, quite a recent paper. So this is really recent stuff that we're starting to understand. And if you've ever been to a public aquaria, you'll have seen many fish in them. And many elasmobranchs, or sharks or rays, if you like, are easily trained. And it requires a certain level of cognition to be able to be trained to the degree that they are trained in captivity. They are trained to do a variety of things, in as much as the same training would be carried out on higher mammals, higher vertebrates rather. So, for example, showing their body, responding to target training, all sorts of things that you would expect higher vertebrates to be able to do. Fish and elasmobranchs, because they aren't the same thing, are able to do also. So cognition is generally seen as an adaptation in the animal kingdom. Natural selection has favoured cognition to solve common problems like habitat complexity, like the goby example. Predator avoidance selection has favoured quite cunning and cognitive abilities to escape predation. Foraging, but also the breadth of diet is also linked to high cognition in many complex animals. Mate choice and intra and interspecific communication is a very complex set of properties and behaviours which again requires at least a certain level of cognition. Sociality is very, very strenuous on one's brain, as I'm sure many of you will know, especially if you're very socially active. It can be quite difficult keeping track of who's doing what, when and where. And fish have to go through these same processes. It's also been shown that some fish and some invertebrates can solve problems and use tools and so on. And they do possess working and episodic memories. So all of these ideas which normally relate to high cognition in terrestrial fauna are selection pressures in aquatic fauna as well. There's no reason why the same results under natural selection will not occur. And to give you a very brief example, the habitat complexity of a coral reef system is immense. It's incredibly complex. There's lots of different heterospecifics, including invertebrates, all of a weird and wonderful colour, all trying to eat or kill each other for one reason or another, all trying to mate with each other. It's a very, very complex environment, and as a result, high cognition is required just to be able to stay where you are and to make a living on a general basis. But there might be another route to high cognition in aquatic animals. The information I just gave you related to specific adaptation to an issue in their natural habitat which they are solving via high cognition. High cognition may also be an emergent property from other physiological adaptations, and the cephalopods are a great example of that. Now, if you can, as soon as you see the cephalopod in this video, I want you to put your hand up, okay? There's a little guy talking at the beginning, so you can ignore that. But soon, it'll pan to a shot where there's an octopus hidden, okay? And I want you to see if you can find it. And this is Roger Hanlon, who's an expert in cephalopod behaviour. You may have seen that video before, but it shows a remarkable ability to transform itself, and the neural complexity required to activate that physiological response is absolutely immense. And they're very, very complex chromatophores, which are individually controlled by different muscles. They're also able to match the texture, the background, the colour, the shape, and their behaviour also sways in line with the seaweed in this example. And the level of neural complexity, which is what I'm trying to get across, is absolutely remarkable and very, very high. And you can see how remarkable it really is. And this is common amongst cephalopods. Apart from the nautiluses, many species of octopus and also cuttlefish are able to do very, very similar things. So high cognition might not be the result of simple problem solving in a natural environment, but might actually be an emergent property of something else. Now, as I say, the neural complexity required to do these physical aspects is immense and might lead to sentience as an emergent property rather than being selected for per se. So there may be two routes to high cognition within the aquatic fauna. And of course, you don't see this in terrestrial organisms. It's far more interesting, from my point of view, exciting behaviour than you'll find in your average terrestrial vertebrate or invertebrate. Another example of remarkable cephalopod physiology which adds to their neural complexity is this what's called a split signal. And we took this photograph for a paper that got published last year. And male cuttlefish will use this intense zebra patterning, as it's called, to attract females or ward off males. Now, these cuttlefish are able to do an intense zebra pattern on one side, but also mimic females on the other. And this is a good example. This is a slightly different species. This is Sepia officinalis, which we find in our waters all over the place. And you can see in this instance here, the male is signalling to the female that he's a male and wants to reproduce, but he's signalling to another male that he's a subordinate male or a female and wants to be left alone to a varying degree. Now, this might seem quite straightforward, but the complexity requiring split control of your body is really, really difficult. It's not simple at all. Imagine trying to independently, without thinking, controlling your left and right arm. It's hard enough for us to do anyway, but to do it over your entire body is really, really remarkable. And it really does involve their entire body, or at least the epidermis and all of it, because each of these little cells which are able to change colour and texture are called chromatophores. And they are cells that have a ring of muscle around them. So every one of the cells used in this has a muscle that requires contraction of some kind or another. So again, hopefully we're getting across this idea that the complexity in cephalopods relating to their initial anti-predatory camouflage has led to this remarkably complex and emergent property of cognition and possibly sentience as well. And that doesn't really end there. We do know that control of octopus arms can be absolutely independent from one another and also the central brain area. And this is published in Science in 2001, so reasonably old now. But it shows you quite clearly that through experimentation they are able to control each arm independently from one another. Again, the complexity of that is remarkable, and as I say, this possibly leads to the emergent property of intelligence or sentience. So hopefully I've given you some good reason to think why aquatic animals are intelligent, and the good evidence for why it might have evolved or it might be an emergent property. Now everyone loves a good quote to take home with them, so there is every reason to expect highly intelligent aquatic species, and you can quote me on that, okay? So hopefully I've at least convinced some of you that it is a thing. But you don't actually have to take my word for it. There are lots of examples where the behavioural manifestations of high cognition have been reported frequently. But again, hopefully you'll notice that 2012, this is a very new paper, relatively speaking. This is a group of fish called the wrasses in the Labridae family. And these guys have been shown to use tools. A special type of tool, they use an anvil. And if you may remember, I guess you guys are quite a lot younger than I am, but one of the first examples of chimp tool use, which everyone saw on The Living Planet, or no, The Natural World, with David Attenborough, was about chimps using anvils to smash open objects that were too hard to eat from otherwise. We now have very clear video evidence of wrasses doing exactly the same thing. These wrasses take a clam, or whichever species is preferred, and will swim quite far to find their preferred rock, which shows a level of understanding that this rock is particularly useful. And the rock itself will be used as an anvil. The fish, the wrasse, will take it all the way and start smashing it against the rock to get inside the clam or bivalve or whatever it is to access the food. And we sort of take this a little bit for granted now because we've seen chimps and other species do it as well, but this is really, really remarkable. Aquatic animals don't need dexterous, opposable thumbs and fingers to use tools. They're able to use what they have available, which is their mouths in this instance. And again, this has been published in a peer review article, so it's gone through a degree of rigour, and we have some confidence that this is a real thing. And this is far from the only example of tool use in aquatic animals. Again, to look at cephalopods, Current Biology is a very high impact factor journal, very, very rigorous, very difficult to get published in. And this account is now quite famous. You'll see lots of YouTube videos of this blue-veined octopus carrying around different parts of shells in an anti-predatory way. And the octopus will walk around with these shells and not only use them as a one-off, like a refuge, like a cave, or hiding in a tree, like many animals would do. They're able to show, or they're able to predict to some degree what will happen in the future, and that is one of the definitions of using a tool, is that you have an understanding of when it will be useful. So these aren't born with coconut shells on their back, you have to go and find them. They don't always find them, quite often there won't be enough there. But nevertheless, these octopuses do carry these mobile homes around with them, which again is a great example of defensive tool use. Again, even more remarkable because these are invertebrates. Octopuses don't have a central brain, they have a brain which their stomach passes through, so it's donut shaped, and they have lots of little clusters of ganglion around their body, and as a result they are able to do these remarkable behaviours based on their high cognition. This is a very, very new example. This hasn't been published yet. And I believe this comes from actually a conference proceeding, but it will be written up quite soon. This is an example of possibly, although it's quite difficult to tell from the video itself, these octopuses are probably, well I say probably, more like possibly, using projectile weaponry to ward off one another. They live in a very densely populated area, and octopuses are generally very solitary. And they've been shown to, or at least it looks like, they're actually throwing shells at one another. And I don't think in any other species on the planet, projectile weaponry has been shown as an example of behaviour. So again, remarkable behavioural complexity, remarkable foresight, remarkable use of tools by an invertebrate. But it doesn't end there. We're all very well aware, or hopefully if you're not aware, that actually seeing yourself and recognizing yourself in a mirror is one of the higher traits available to the most complex cognitive organisms. There's only a handful of animals on the planet that have been shown to have self-awareness in a mirror. Of course, chimps are very famous for it. I think dolphins have also been capable of it, and there's one or two, possibly other examples. Corvids may be able to do it. But here we have evidence that a manta ray is able to do it. The PhD student put a mirror in front of the aquarium, and this particular ray would frequently swim up to it and check its underside, which coincidentally is exactly what a chimp would do if you provided it with a mirror. It would be aware enough of itself to think, is this me? I'll turn around and have a look. And this is exactly what the manta ray is doing. Okay, this is still fairly hot off the press. It's only 2016, May last year. So this is far from accepted in the scientific community, but nevertheless, it's the beginnings of a fantastic avenue of research looking at self-awareness in a manta ray, which nobody would have ever predicted 2 years ago, never mind 5 or 10 years ago. So hopefully this is reasonably compelling evidence that it's at least worthy of investigation, although there's a lot of work to be done. And it doesn't end there. Referential gesture in fish collaborative hunting. Now, referential gesturing is actually using your face to point at something or to suggest an animal looks somewhere. These 4 or 5 different species, completely unrelated species, including an octopus species, actually use facial indications or facial signals to signal to one another where the prey is. For example, the grouper or the eel would push a prey out of a hidden rock place. There'd be another fish watching, and it would direct the behaviour of yet a third species to where the prey was, okay? Which is absolutely remarkable, and it's been published in Nature as a result. So you don't see this in terrestrial vertebrates. You might see some collaborative hunting between 2 species, but not to the complexity of 4 or 5 species working together to solve a very common problem, i.e. foraging. So given that I've hopefully shown that fish are high, or aquatic animals have high cognitive abilities, does that mean that they're able to suffer just like we're able to suffer? We put our suffering down to being intelligent and being emotionally aware. So what is the evidence for suffering in aquatic animals? And I'll start with fish, so I have separated these from all other aquatic animals to start with. Well, this is a table actually I stole from Wikipedia, but I'll fill in the gaps in a second. There's actually the Wikipedia page for fish suffering is actually very, very thorough, and the references are really good, and it's worth checking out if you don't have a lot of time. For a long time, we've known that mammals, birds, and reptiles have nociceptors. They're simple cells on your epidermis which will cause a flinch reaction if you're enduring negative stimuli. Okay? They move you away from the stimuli. Now, that does not equate to feeling pain. It just shows a flinch reaction. Nematodes, for example, have nociceptors. I will never try and convince you that nematodes can feel pain. To feel pain, the nociceptors needs to have a brain to attach to, and also has to be linked from the nociceptor cells to the brain. So these 3 are fairly linked, and they've been shown conclusively in mammals, birds, and reptiles, and we've known this for a long time. Other suffering animals we accept that suffer produce endogenous opioids, and these are a response to pain, for example. They're also a reward chemical when you've done something right. We all have opioids in our system or similar chemicals, and again, these are found across the animal kingdom, including mammals, birds, and reptiles. Analgesics is a complicated name for painkillers. We know that painkillers work in mammals and birds when you hurt them. We don't know about it in reptiles or amphibians yet. And, of course, response to damaging stimuli by similar to that of humans. And this can include licking or being very gentle with the wound, for example. It can involve cowering away from the stimulus. It can involve hiding from conspecifics. Very similar to behaviour that you'd expect from a human if you hurt them significantly. Again, obviously, mammals, we've seen it, birds, reptiles, and amphibians. So what about fish? Where do fish fall within this? Well, you might be surprised to know that there is strong evidence for all of these categories, which we now always assume are enough for mammals to feel pain, and birds and reptiles. Except we don't know enough about amphibians and reptiles when it comes to analgesic effects. Now, I'm not going to bother giving you a reference for it has brains, so hopefully you at least assume fish have brains. But nevertheless, these are well-established peer-reviewed publications showing that just like mammals, fish have nociceptors, they're linked to a brain, they produce opioids themselves, analgesics or painkillers work on them, and they respond similarly to humans when damaged. So to break this down even further, and this is quite an important point I feel, because cartilaginous fish, which are the sharks and the rays, are as dissimilar to bony fish as birds are to mammals, yet we group them continually all the time. they are far more derived from one another than birds and mammals are. Birds and mammals separated, I think, 250 million years ago. Cartilaginous and bony fish separated nearly 1 billion years ago, if not more. So they are so different from one another that it is completely inappropriate to lump them together. And the evidence is missing for lots of these subsections of a criteria which I showed you before, which we know most about for bony fish. And one of the more interesting aspects of this is that we've actually shown that fish will self-administer analgesics given the opportunity. Now, can anyone think how that might play out? Well, it actually leads to a form of drug addiction. These fish realise that their analgesics give them a good feeling, and they will self-administer and become rather annoyed if they're unable to access their analgesics, which is really, really unusual. Something no one ever expected. But again, there's a good paper showing that fish will self-administer analgesics given the opportunity, which to me is very, very interesting and suggests that there is some positive aspect related to feeling within the organism, because that's what analgesics do. They temper the feeling of pain. Some analgesics, the morphine-based ones, do give us pleasure. So it's possible, and of course we can't know what fish is feeling or thinking, it's possible that these similar drugs are acting in a similar way to fish, much as they do to humans. So what about the invertebrates? Well, I talked about cephalopods quite a lot, and obviously they're going to be coming up next. And in 2013, the EU decided, alongside the UK government, that as a result of cephalopod evidence being extremely similar to that of fish, the criteria used for fish pain, that they would be protected under UK and EU law when it comes to their use in science. So there's enough evidence for us to require very strong and difficult to get licenses for causing suffering or pain in these organisms. And this has been reviewed a lot now. There are lots of papers saying similar things, showing similar things. And as I say, as a result, they are now protected in science, just like all vertebrates are in the EU and the UK. Interestingly, the EU and the UK weren't the first to protect them. They were protected already in some Scandinavian countries and some Australian states as well. And we consider ourselves quite progressive when it comes to animal welfare laws, and we are. But again, Scandinavian countries and some Australian states have already protected decapod crustaceans as well. And there is a strong move to begin this idea of decapod crustaceans may feel pain and they should be protected as a result. And I work quite strongly or quite closely with some EU legislators, and at the time they protected decapod crustaceans, there were actually more evidence available, and there was a bit stronger feeling that the crustaceans would be protected and the cephalopods wouldn't. No one's quite sure why it switched around, and we protected cephalopods and not crustaceans at that time. Nobody will ever know. And talking about invertebrates more, and decapod crustaceans in particular, and these include shrimp and notably lobster. If you've ever cooked lobster, I would hope that you euthanize it first now, because we do feel that there's a strong possibility that lobsters, like all decapod crustaceans, will likely suffer. And in science, we use what's called the precautionary principle, where if the data is not quite there, and we generally, especially in welfare science and in the use of animals in science, the precautionary principle says we tend to give the benefit of the doubt to the organism, because it's much easier to protect it than it is to reduce or remove the pain that you've already given it. And speaking of pain, there is some papers, again very recently, who was this one? It wasn't quite there. I think it's 2013, that there seems to be shock avoidance and discrimination learning in the shore crab, which the authors argue may be a sign that they can feel pain from the electric shock. And again, there's a couple more papers coming out which take this further and provide possibly stronger evidence that things like crabs and lobsters and shrimps might be able to feel pain. So I do hope that at the very least you'll consider treating decapod crustaceans a little more humanely until we know for absolutely certain that they are unable to suffer. And as it stands, it's looking like they can suffer. So I must be honest, I'm a scientist, so you have to take evidence where it is. And there's still quite a heated debate about all of this, whether or not fish can feel pain, whether or not decapod crustaceans can feel pain. There's certainly no 100% consensus. In my mind, and speaking to the various scientists and the community at large, it's like climate change was 10, 15 years ago. 90% of the community accept it. There's still an argumentative, vocal 10% who generally have vested interests will not accept it. And if you are interested in the counter-arguments, Rose in particular is adamantly against the idea that fish can feel pain. However, he does have links to the fishing industry, so it's very, very difficult to know what his motivations are. He does get paid by the Angling Society, I think in the US, but do check that out for yourself, okay? Make your own mind up. So, if you accept some aquatic animals are highly intelligent, and the evidence suggests that they can suffer, and most importantly, you can see past the phylogenetic differences, so you stop seeing them as alien and you try and empathize knowing these facts, then you start to see a lot of poor welfare everywhere. And it is a major problem, and getting this information to the relevant people can be very, very difficult. There's a lot of resistance to the idea that fish can feel pain and suffer, because an entire industry, the hobbyist sector, it would affect them massively. So there's a lot of money involved in the other side of the argument, if you like. And I'll give you some evidence or some examples of poor welfare. And I worked on thornback rays. Anyone seen these before? I would have thought so. They're common in the UK. They are protected under CITES. You do find them a lot in public aquaria. And they reproduce quite well in captivity, although rarely are they reintroduced. And this is what they do. They sit on the bottom of the ocean or the sea. They are highly adapted to a flat, pressed-like behavior on the ocean. They forage by gathering invertebrates out of the sediment or the substrate, or scavenge. Okay, it's really important that you realise that these are fantastically adapted to that sort of lifestyle. They really are quite well remarkably adapted. Their eyes have moved. There's a long natural history and selection processes to get them like that. However, unfortunately, has anyone seen them like this in captivity? This is unnatural behaviour, okay? These rays do not swim like this in the wild. There is no evidence that they ever swim vertically. However, this is seen as an attractive, appealing pose in public aquaria. They look like little angels, it looks really cute, kids love them. And aquarists actually encourage this behaviour. We suspected this was a stereotypic behaviour. It was a behaviour that had no normal function and was highly repetitive and was the result of a stressed environment. So we tested that idea, as good scientists try to. But first of all, we looked at the literature, as you always do, and lo and behold, from the aquaria community, a paper came out, surface breaking behaviour in a population of captive rays, the expression of a need to forage. Now that's not how rays forage at all. Surface breaking is when they come up to the surface and either try and jump out of the tank or spiral around in circles. None of these are natural behaviours. You'll never see this in the wild at all, but yet people are trying to convince other scientists that this is a natural behaviour and therefore can be quite happily encouraged, which I was very, very sceptical about, knowing that these are flat animals that hover around the seafloor, scooping things up, and have no need to spiral up and down, which looks completely unnatural. And I think it is. Again, just to remind you, that's a natural behaviour. To me, that doesn't look like a natural behaviour. However, evidence is more important than my comments. So, myself and an undergraduate student at my last position, we created an ethogram like all good welfare scientists do, and we noticed that there were lots of different unusual behaviours. Now, thigmotaxis is known as the fear of open spaces, and it's one way of measuring poor welfare in animals. And we noticed that quite often they would rest on the side of the tanks like this. So it was called vertical resting. Vertical swimming was when they were swimming just up and down like this. Again, not a behaviour you'll see in the environment. They also try to bury themselves at the side of the tank as well, and this is called, or this could be called, a vacuum behaviour, where they're trying to do normal behaviour but in inappropriate circumstances and continually doing it because they are unable to do it. And we had all sorts of stuff which, again, we are convinced are genuine stereotypic behaviours like surface breaking and or spiralling, which they just don't do in the wild. So we investigated why, or rather, when would you see more evidence of these behaviours in what circumstances? And we tested a variety of scenarios. For example, we looked at different substrates, because in the wild they tend to go on the same substrate all the time, but in public aquaria they often give them bare tanks, no substrate whatsoever. They often give them gravel and sand. And we found that the proportion of the time resting varied on, with relation to the substrate. Now, in the wild, they rest an awful lot. If they're being active in captivity, that's not a good sign. We have this idea that we should be increasing activity of animals in captivity because it must be good for them. But actually, it's not. If an animal sits there and does nothing for 23 hours and 59 minutes a day, then that's what it should be doing. And we found that in different substrates, that the level of time resting or not resting increased. So we had an idea of which substrates they preferred. Also, we tested different depths of substrates and things like this. But the real interesting result was that stereotypic behaviour, which was one of them was bobbing, was much or significantly higher when they were in higher stocking densities. And again, this fits the natural history of these organisms. They come together rarely and only to breed. They do not live with each other in the wild. Now, putting them in unnatural densities seems to be encouraging these stereotypic behaviours. So we found a nice link between inappropriate conditions and an increase in these stereotypic behaviours. But unfortunately, this paper's been out nearly 2 years now, or just over a year. Not a single public aquaria has adopted or acknowledged these results or taken them seriously. And this is a common problem we have. I also run a website called zooscience.com, and the whole point of it is to collate welfare papers in a zoo community and then give them to the keepers and aquarists because they don't have access to them. Once you leave university, you take for granted that you lose or that you've had access to Web of Knowledge and to other very, very valuable resources. So maybe it's because they haven't had access to this paper yet, although I know that's not true because I've been, giving it to them en masse anyway. But nevertheless, it's a shame that as a welfare scientist, we don't see our interventions or our evidence-based interventions taken care of or utilised. And it's probably always about economics. It costs money to change the substrate in the tank. Of course, with the stereotypic behaviour, it's been unwittingly, hopefully, actively encouraged because it makes a more interesting experience for the visitors, when in fact it's a stereotypic and therefore negative behaviour which should be discouraged. And convincing staff to prevent something that the public seemingly enjoy is really a very difficult task. And to show you some evidence of this in action, many public aquaria have diving with animals, for example. I think this is possibly a terrible idea. This ray, again, is doing the vertical resting or the vertical bobbing, and this ray is in terrible condition. You can see the asymmetry in the development. It's had a very difficult developmental period. It's got damage here, it's got shredded tails and so on. But this is a publicity photograph for a particular public aquarium in the UK. They don't even know what they're showing us. They're showing us a stereotypic behaviour of a damaged animal, and they just don't know. They're not aware of it. And touch pools are very encouraged in the UK, and especially the US and other countries. And the children are poking the animal and touching it and stroking it because they think stroking it is okay, when in fact the ammonia that we have on our hand burns these animals. So not only were we encouraging it, but we're actually exacerbating the problem hugely as well. So this is a very major problem that we find. And to give you further examples of stereotypic behaviour, it's fairly well known that captive sharks pace. Now you might be aware of animals pacing, particularly in zoos, big cats, you see them going round in circles, that's known as pacing. Well, sharks do exactly the same. No matter the complexity of the tank, the size of the tank, the shape of the tank, they just swim around in circles all day long. And this leads to physiological changes, deformities in their spines, which again is a published paper, good evidence, reasonably rigorous peer review, showing that pacing leads to deformity. But again, it's very difficult to convince owners of these animals that things need to change. And I had this idea where if I use crowdfund, I think it was, yes, crowdfund, I didn't really get anywhere. Even though I was allowing someone to name my ROV Rovy McRovy Face, and nobody bought it. The idea was to buy an ROV, modify it, add some small pieces of Adreno shields to get water quality samples and so on, but more importantly, to drag food around and get the shark to swim in different directions, to use the entire tank, to really get it to use its captive environment more than it's doing now, to hopefully reduce these stereotypic behaviours, or you can't remove them once they're established, but reducing them and adding some complexity to its life. Ordinarily, it just gets fish chucked into the tank or hand-fed by visitors. A shark doesn't want to be fed; it wants to hunt. To quote Jurassic Park, I'll paraphrase it. And by using this ROV, hopefully, it would swim around very quickly and engage the shark in a way that it's not presently being engaged. Now, I still hope to do this one day, and I really want to do it with Anglia-Ruskin students, because although I have a reasonable idea of what to do, I think the younger generation are much better at coding than I am and dealing with things like this. So if I ever get this off the ground, it'll certainly be part of a Anglia-Ruskin students project. It'll be a non-credited project, but nevertheless it'll be quite fun to do, hopefully. So I want to talk very briefly about why aquaria also may struggle. Aquaria are considered by zoos, are considered as zoos under the Zoo Act, for example, so they're treated the very same way. But aquarium animals are far, far, far harder to look at. Not only do you have to adjust atmospheric temperature, as you would do for mammals, but all of these massively complex variables need to be reasonably maintained to ensure that animals don't get ill or are actually poisoned. And it's a very complex process. If you've ever kept a reef tank, it's a nightmare. It's really, really difficult. It can take a huge amount of your time making sure that the conditions are acceptable, which terrestrial zoo staff don't have to do. These are not issues that are faced. In addition, the complexity of life support in public aquaria is fantastically complex. This is a part of what's called a plant room, which deals with the life support systems. Now, in an average public aquaria, the plant room will be like 4 or 5 of these rooms in surface area, all with technology like this, of varying ages and varying likelihood to fail at any given moment, which it does as well. It fails and the entire tank will die out very quickly. Fantastically complex. So you get the idea, I think, that your average aquarist, which is equivalent to a keeper in a zoo, has far more on their plate than your average zookeeper would have. And of course, public aquaria don't employ more staff as a result. Okay? So the animals aren't getting checked to the same degree as they would do in a zoo, or at least that's a working hypothesis as to why welfare in aquaria is generally lower than it would be elsewhere. There's also a problem of too much diversity. A zoo might have 3 phyla, which includes a chordata, which is us, vertebrates, mollusks and arthropoda. There may be a couple of unusual examples, but generally speaking there's 3. Aquaria will have at least 9. Annelida, so they have worms, which are often on show, but the really complex ones like Cnidaria, and the corals and the sponges, of course, are fantastically complex organisms, really, really difficult to understand, much harder to keep than your average mammal, for example. So the difference between zoos and aquaria is quite stark when it comes to investment in welfare. And there's also a philosophy at the moment where 90% of marine animals in public aquaria are wild caught, which would not be acceptable in a terrestrial environment, but is the norm in an aquaria, which is completely unsustainable. And there are great efforts to move towards a sustainable nature of public aquaria, but we're a long, long way from making all the animals that you see in public aquaria captive bred. It's very, very difficult. There's lots of bottlenecks, they're very complex larval stages, and we don't know what they feed on. Hence, they breed fine in captivity, but the offspring die immediately because they starve to death, because we don't know what we're doing. But yet, time and time again, we'll go and collect them from exotic locations and bring them back, hoping that they stay alive long enough for the public to see them. And I think they have the same solutions as zoos or terrestrial collections, which aren't yet being employed. Environmental enrichment is still relatively rare in public aquaria. There was a fantastic shape of the enrichment course at Brighton Sea Life last week, or the week before, so there are steps moving in the right direction, but this is still one of the very few times that this sort of enrichment course has been run for aquatic animals. You can include feeding enrichment. My idea of an ROV to try and get the shark to do different behaviours is one way of trying to enrich its life. Of course, conspecific enrichment, heterospecific enrichment, all sorts of things you have in terrestrial collections, sometimes you'll find in aquaria, sometimes you won't. And this was taken from a website of ideas. I think it's from the Shape of Enrichment. And all these different ideas are very, very similar. And these are for aquaria animals, not terrestrial animals. And they're just the same ideas, really. And the more, perhaps, that public aquaria emulate good zoos, perhaps the better the welfare will be. And the only real difference I could find between all of these would be the creation of currents during feedings. And I sort of had a bit of a crazy idea that you could have a terrestrial equivalent of that, and you would have lots of dead mice for predators, for example, which you would normally hand feed perhaps, but you get an air blower that you use for leads and you blow these frozen mice around. Although it's a bit ghoulish, nevertheless it does sort of fit with that idea. But the point is that we can enrich these animals' lives. There's lots of already well understood methods for enriching animals' lives, but have yet to be employed en masse across public aquaria, not just in the UK, but also the world as well. So that's the end of my talk. Thank you very much, and hopefully you'll have a better appreciation of our aquatic pals. Thank you.